Preface. The microprocessor has been with us for some 15 years now, growing from an awkward 4-bit child to a robust 32-bit adult. Soon, 64 and then 128-bit wizards will appear to crunch numbers, spreadsheets, and CAD CAM. The engineering community became aware of and enamored with the 8-bit microprocessors of the middle to late 1970s. The bit size, cost, and power of these early CPUs were particularly useful for specific tasks involving data gathering, machine control, human interaction, and many other applications that granted a limited intelligence to machines and appliances. The personal computer that was spawned by the 8-bit units predictably became faster by increasing data word size and more complex by the addition of operating system hardware. This process evolved complex CPUs that are poorly suited to dedicated applications and more applicable to the generic realm of the computer scientist and system programmer. Engineering applications, however, did not change. These applications continue to be best served by 8-bit CPUs with limited memory size and I/O power. Cost per unit also continues to dominate processing considerations. Using an expensive 32-bit microprocessor to perform functions that can be as efficiently served by an inexpensive 8-bit microcontroller will doom the 32-bit product to failure in any competitive marketplace. Many designers continue to use the older families of 8-bit microprocessors. The 8085, 6502, 6800, and Z80 are familiar friends to those of us who had our first successes with these radical new computers. We know their faults and idiosyncrasies. We have, quite literally, tons of application software written for them. We are reluctant to abandon this investment in time and money. New technology makes possible, however, a better type of small computer, one with not only the CPU on the chip, but RAM, ROM, timers, UARTs, ports, and other common peripheral I/O functions also. The microprocessor has become the microcontroller. Some manufacturers, hoping to capitalize on our software investment, have brought out families of microcontrollers that are software compatible with the older microprocessors. Others, wishing to optimize the instruction set and architecture to improve speed and reduce code size, produced totally new designs that had little in common with their earlier microprocessors. Both of these trends continue. This book has been written for a diverse audience. It is meant for use primarily by those who work in the area of the electronic design and assembly language programming of small dedicated computers. An extensive knowledge of electronics is not required to program the microcontroller. Many practitioners in disciplines not normally associated with computer electronics transportation, HVAC, mechanisms, medicine, and manufacturing processes of all types can benefit from a knowledge of how these smart chips work and how they can be used to improve their particular product. Persons quite skilled in the application of classical microprocessors, as well as novice users who have a basic understanding of computer operation but little actual experience, should all find this book useful. The seasoned professional can read Chapter 2 with some care, glance at the mnemonics in Chapters 3 through 6, and inspect the applications in Chapters 7, 8, and 9. The student may wish to quickly read Chapter 2, study the mnemonics and program examples carefully in Chapters 3 through 6, and then exercise the example programs in Chapters 7, 8, and 9 to see how it all works. The text is suitable for a 1- or 2-semester course in microcontrollers. A 2-semester course sequence could involve the study of Chapters 1 to 6 in the first semester, and Chapters 7, 8, and 9 in the second semester in conjunction with several involved student programs. A 1-semester course might stop with Chapter 7 and use many short student assignments drawn from the problems at the end of each chapter. The only prerequisite would be introductory topics concerning the basic organization and operation of any digital computer and a working knowledge of using a PC-compatible personal computer. No matter what the interest level, I hope all groups will enjoy using the software that has been included on a floppy disk as part of the text. It is my belief that one should not have to buy unique hardware evaluation boards or other hardware-specific items in order to try out a new microcontroller. I also believe that it is important to get to the job of writing code as easily and as quickly as possible. The time spent learning to use the hardware board, board monitor, board communication software, and other boring overhead is time taken from learning to write code for the microcontroller. The programs included on the disk, an 8051 assembler named A51 and a simulator named S51, were both written by David Akey of Pseudocorp, Newport News, Virginia. Pseudocorp has provided us all with a software development environment that is not only easy to use, but one that we can uniquely configure for our own special purposes. Details on the assembler and simulator are provided in the proper appendixes. Use them as early as possible in your studies. Many points that are awkward to explain verbally become clear when you see them work in the simulator windows. Further information on products developed by Pseudocorp follows this preface. I have purposefully not included a great deal of hardware-specific information with the text. If your studies include building working systems that interface digital logic to the microcontroller, you will become very aware of the need for precise understanding of the electrical loading and timing requirements of an operating microcontroller. These details are best discussed in the manufacturer's databooks for the microcontroller and any associated memories and interface logic. Timing and loading considerations are not trivial. An experienced designer is required to configure a system that will work reliably. Hopefully, many readers will be from outside the area of electronic design and are mainly concerned with the essentials of programming and interfacing a microcontroller. For these users, I would recommend the purchase of complete boards that have the electrical design completed and clear directions as to how to interface common input-output circuits. Many people have played a part in writing this book. Special thanks go to all of the following people: the reviewers of the early, really rough drafts of the text: Richard Barnett, Purdue University; Richard Castellusis, Southern College of Technology; Jerry Cockrell, Indiana State University; James Grover, University of Akron; Chris Conant, Broome Community College, New York; Alan Cacchetto, Alfred State College, New York, for their thoughtful criticisms and words of encouragement; Cecil A. Moore, Staff Applications Engineer for Intel Corporation in Chandler, Arizona, whose meticulous comments have greatly improved the technical accuracy and readability of the text; Tom Tucker of West Publishing for his willingness to experiment; and my wife for many years of patience and understanding; my students, past and present, who have taught me much more than I have taught them. Finally, let me thank you, the reader. I would be very grateful if any errors of omission or commission are gently pointed out to me by letter or telephone. Thank you for your help. Kenneth J Ayala, Western Carolina University, Cullowhee, North Carolina.